Good evening and happy Thursday. We will be finishing up the first unit today. All right, so you should have already seen that the first test posted. All right, so there's no quiz for tonight. Instead, there's the first unit test. What did we look at last time? I think what it was, right, behavior of graphs, right? So we looked at graphs of functions, how it behaves, right? So increasing, we looked at average rate of change. Saw that was also the slope of the secant line between the 2 points, the endpoints of the interval. And we also looked at combining functions, right? Adding, subtracting, multiplying, dividing, as well as function composition. This evening, we're going to look at transformations of functions. Right, so there are 3 broad types of transformations. There is the translation, there's a reflection, and then there is a stretch or compression. We will also look at a special type of function called one-to-one. And we will look at what we mean by the inverse of a function. So starting with transformations. I'm going to start with the translations. All right, so let's consider the function that is obtained f of ax plus b. All right, so B results in a vertical translation. Excuse me for a minute. Okay, sorry about that. So the value B is going to result in a vertical translation, right? If B is positive, how do I want to word this? Then G of X is and so if B is positive, then G of X is just a vertical translation of f of X. Absolute value of B units upwards. All right, so it just shifts the graph of f of X B units upwards. If B is less than 0, right? Then f of x is shifted, absolute value of b units downwards. Right, so that value a is going to result in a horizontal translation, either left or right. If a is positive, then f of x is shifting to the left by a units. Right, now if a is negative, then f of x is going to shift absolute value of a units to the right. In the positive x direction. So be to the right as you're looking at the plane, the coordinate axis, that way. Right, so everything is with respect to the coordinate axis. That happens if a is negative. If a is positive, it's a leftward translation. So the horizontal works the opposite of what you would think, right? Because you think if you go to the right, it's a positive movement, right? So you would think a is positive, but it's not. So the horizontal works in the opposite of what you would think. Positive is left, negative is right. I'm sorry, that should not have been a times x. That should have been x plus a. Now look at b times f of ax. call it distortion. Wow. So B is going to result in a vertical stretch or compression. Again, depending on the value of B. This is a vertical compression of f of x. Right, so if B is between 0 and 1, what we have is a vertical compression of f of x by a factor of 1 over b, right? So if b is a half, then f of x gets compressed vertically, right? So you're squeezing it in the vertical direction by a factor of 2. If b is larger than 1, then it is a vertical stretching by a factor of b. Notice that b is positive, right? If b is negative, we just look at the absolute value of b. For the stretch or compress, the negative tells us something different, which I'll look at right after I look at the a value. Turn this on to right. So A is going to result in a horizontal stretch or compress. If A is between 0 and 1, we have a horizontal stretching by a factor of 1 over A. Again, so the opposite of what you would think. And if A is greater than 1, you have a horizontal compression by a factor of A. The function negative f of x is a reflection of f of x about the x-axis. In other words, it is a vertical reflection. The function f of negative x is a reflection of f of x about the y-axis, right? So it's a horizontal reflection. Okay. So those are our three types of transformations: translations, distortions, I guess, stretch compressing, and then reflections. So what we're going to be asked to do for the first 4 problems is to use the graph of the absolute value of x to sketch the graph of the given function. Good enough for government work. That is what the absolute value of x graph looks like. It's just a V, right, with the vertex at the origin. absolute value of x minus 1, right? So this here is our f of x, right? So what type of transformation is this? Is it a translation, stretch, compress, reflection, or is it a combination of them? Okay, we have reflection, we have translation. So for reflection, is the function being multiplied by a -1? It's not, right? It is a translation. What kind? Horizontal or vertical? So for horizontal, it have to be of the form f of x plus a. Isn't this f of x plus b? Right? It's vertical because look, we're changing after the output, right? So what we're changing is the output, not the input. So first we evaluate f of x. That gives us the range. Then we subtract 1. So this winds up being a vertical translation down by 1 unit. I have an example of that coming up. So then that would be the graph of absolute value of x minus 1. Y is positive, yes. Well, I mean, y can be negative, right? So remember, y is just the output value, so it would be negative down here. But then the values of positive would be everything above the x-axis. absolute value of x minus 2. Let me see if I can do this. And there we go. So if we look at this, this would be f of x minus 2, wouldn't it? Because we're dealing with absolute value of x. So notice what we're doing this time is we're affecting the input. And so we're affecting the domain. This would be a horizontal translation. Now the question is it to the left or to the right? It'd be to the right. By 2 units. So we'll just say that is 2 units. Not want you to move. Just a little bit more. That should be. Okay, that should be good. And that is what the absolute value of x minus 2 would look like. Yes, that's what I wanted. Copy, paste. And now let me delete these. Oops, no, not you. You. Yes. Okay. Absolute value of x plus 2 minus 1. So look what's happening here. Right? Not only are we changing the output, right? We're also changing the input. So we're going to have 2 translations. Right? As was just stated, it's going to be 2 units to the left and then 1 unit downwards. Let's say that is 2, and I don't know, say that's 1 there. And where they cross is my point. All right, so that's where the new vertex is going to be. And now it's just I wish it would stop doing that. And so that would be this function. Right? -2 times the absolute value of x plus 3. Well, we got a lot going on here. So technically speaking, the translation up 3 is going to be the last thing that happens. Right. Well, this negative here, it's going to reflect about the x-axis. Right, so now we're going to have an upside down v. That 2 gives us a vertical stretch by a factor of 2. And then it'll move up 3 units. The 2 is a stretch. The negative tells us it's going to reflect. Right, so what we're really doing is we're writing this like this. -1 times 2 times absolute value of x right? In which case the B now is 2, so it's positive. And then that negative tells us it's a reflection. Right, so that's why, remember when I was listing out the types, we only ever considered values of B or A that were positive. Right, so here we have all 3 types, right? Oh, I don't like that. Let's say 3 is up there. Sketching the stretch or compression is actually quite difficult. So what I'm going to do in scratch work is I'm going to set this equal to 0 and find the x-intercepts, just so I have some extra points to plot so I can get a more accurate sketch. So absolute value of x would be 3 halves, right? So we're going to go positive 3 halves and negative 3 halves at the x-axis. Let's say that's 1. Let's say that's 2. 1, 2. So it's going to cross the x-axis at those 2 points. And then the vertex is here. I'm not going to have a 45 degree anymore. Is it going to be 60? No. Looks like 65 is going to work. And I did not draw this to scale, because of course I didn't. That's okay, because then here's what I can do. Wait a minute. That's definitely not right. Will this work better? It's closer. Oh, I think I see why. Whatever, good enough for government work. Okay, so there is that. Let's see. I want to see how well the calculator is going to be able to do this. So ABS is the command for absolute value. So there is absolute value of X. Next one was absolute value of X minus 1. Then we had absolute value of X minus 2. Was then absolute value of X plus 2 minus 1. Why did I hit enter? I meant just hit down. And then it was negative 2 times the absolute value of X plus 3. Now I can hit enter. Goes like that. There we go. That looks kind of good. So our sketches look pretty good. Is it under tools? I think it is screen capture. There it is, capture page. Okay, so there is the absolute value of X plus the 4 transformation problems we did. So any questions on those 4? Okay. The next word is going to deal with square root of X. Vertical stretch or compress. I will actually be, no, I will not be looking at that. So it looks similar to a vertical. Oh wait, vertical. We did vertical. Are you're asking about what a horizontal stretch or compression would look like? It's very similar to a vertical, right? So if you were to stretch, for instance, absolute value of x horizontally, it would have a similar effect as to compressing it vertically. I would tackle it the same way. I would, instead of trying to find x-intercepts, though, I would just try and plot a couple extra points. Right, so I would just pick several values of x, find their y value, and plot those points just so I can get a better representation. It would be something like this. So if I wanted to, this was a stretch. So if I wanted to stretch this horizontally instead of vertically by a factor of 2, I would do this. Absolute value of 1/2 x. This would be a horizontal stretch by a factor of 2. I want to be careful when I say absolute value. For this case, yes, because the original function was the absolute value of x. It's more so to do with whatever the function is, right? So if what you're multiplying is the input, like in this case, then it's horizontal. Same thing with add. Like if I add a number inside, then it's horizontal. Because what you're affecting is you're affecting the input. You're changing the value before you even put it into the function. Right? Versus vertical, you're changing the value after you've already gotten it from f. So we're working with square root of x this time. That should be good enough. So this is roughly what the square root of x looks like. So now we have the square root of negative x. So first thing, let's just ask, what type of transformation is this? Why do you say stretch? Okay, true, it's multiplication. But what are we multiplying by? Oh, I'm sorry. Yeah, no. What are we multiplying by? One over square root of x. No. Where do you get dividing by square root? Right? That's correct. But why are we multiplying it by itself? The function is square root of negative x. So I think you're doing too much. Since the original function is root x, wouldn't this be f of negative x? Right? So notice what we're doing. We're multiplying the input by -1. Isn't that a reflection? Right? It's a reflection about the y-axis. So just a rough sketch. Looks something like that. So this one. Can what be a function? Yes. But remember, the domain now, x would just have to be negative. So you'd have negative times some negative number. What about negative 3 times the square root of x? And so again, try to write it in terms of f of x. Be negative 3 times f of x, right? So it's definitely going to be reflected about the x-axis. Is that all that's happening? Compressed? Which one? Compressed or stretched? And so let's go back up to the list. A stretch, right? Because it's greater than 1, right? 3 is larger than 1. So it's a vertical stretch. So we're going to stretch it vertically by a factor of 3. Oops. I'm going to say that this tick represents 1 on the x-axis. So when x is 1, we're going to get negative 3. Probably like right there. Right, so we're going to have to go through that point. So maybe something like that. One half square root of x plus 3. This would be what? 1 half f of x plus 3, wouldn't it? Again, f of x is the square root of x. So it's going to be a compression vertically by a factor of 2. And then shifted 3 units to the left. So let's say that would be -3. So when x is -2, y is 1. No, y is a half. It'll be like here. Oh my, yeah, this is going to be fun. Where is it going to cross the y-axis? Square root of 3/2, which is, oh my goodness, which is slightly less than 1. That's going to be like right here. That was going to be fun to draw. I don't know, let's say something like that. Just a sketch. Let me see if I can. If I do that. No, that's not what I wanted. All right, so get rid of you, get rid of you, you. And can I do you? Yes. Can I do you? Yes. That and that. Perfect. For it to sync. Thank you. So negative 1.5 would be negative 3 halves. F of x minus 1. And then plus 2. So again, we got quite a bit going on in this one. We have a reflection about the x-axis, right? That's what the negative tells us. It will be stretched by a factor of 3 halves. Vertically stretched by a factor of 3 halves. Right? And that'll be translated 2 units up and 1 unit to the right. So let's tackle 1, 2, 1. And then I know it's going to go upside down. All right, where is it going to cross the x-axis? X equals. And it's going to cross the x-axis at the point 25/9, which is slightly less than 3. So it looks like that will probably be 3 there. It's going to be slightly less than 3. I don't know, probably be about here. I don't know, something like that. Yeah, so the negative tells you it's going to be a reflection. Where the negative is located dictates whether it is a reflection about the x-axis or reflection about the y-axis. And I'm going to do the same thing. I'm going to go ahead and plot all these in here. So let's start with root x. Next up was square root of negative x. After that, we had negative 3 times the square root of x. After that, is 1/2 square root of x plus 3. And then finally, we have the negative 1.5 root x minus 1 plus 2. Now, these might be better moved. Over here. So again, our sketches look pretty darn good. Okay. Any questions on transformations? Okay, so next we look at inverse functions. So if we have two functions, f and g, and f of g of x and g of f of x both result in just x, then we say that g is an inverse function of f, and we write g of x equals f inverse of x. Okay. Yes, F would also be an inverse of G. Right, and in fact, it is easily shown that the inverse of the inverse is just f of x. Now, because of this right here. Right, so if f is an inverse of g, then g also has to be an inverse of f. Repeat what I just said. If f is an inverse of g, then g must also be an inverse of f. Oh, I'm sorry. That's that's not right. I think I did do that one already, right? So we say that a function f is 1 to 1 if f of x1 equals f of x2 implies that x1 is equal to x2. All right. So what this is saying is that each element in the range has at most one element in the domain that maps to it. All right. So for example, x squared would not be 1 to 1 because both negative 2 squared and 2 squared is 4, but negative 2 and 2 are not the same, right? So in other words, 4 has two elements that map to it, specifically both negative 2 and positive 2. So be careful when you say domain has more than one range. A domain doesn't have a range. A function does. Right. Each element of the range can have only at most one element from the domain that maps to it. So if you think of if you think of a function in terms of a mapping, let's just go simple. Say there's 4 elements in the range. No, let's do 4 elements in the domain as well. That would be 1-to-1. Right? Notice that each element in your range has only one arrow that goes to it. But now if I do this instead, now it's not 1-to-1, right? This dot here has 2 arrows that go to it. There is another way of testing 1-to-1, and that is to look at the graph. We use the horizontal line test. Very similar to the vertical line test, except now you draw a horizontal line. If your horizontal line crosses the graph more than once, it is not 1-to-1. The only functions that have an inverse are 1-to-1 functions. Right? In fact, this works both ways. If a function is 1-to-1, then it has an inverse. Also, if f has an inverse, then it is 1-to-1. Right? So this is your test. If I ask you, find the inverse of a function if it exists, you first want to see if that function is 1-to-1, because if it isn't, there is no inverse, right? So you don't want to waste your time trying to find an inverse. However, just about every function can be made 1-to-1 by restricting its domain. What do I mean by that? All right, so look at x squared. First, consider the domain as all real numbers. Same function, g of x is still x squared, but now notice I changed the domain to be only non-negative real numbers. Right, so 0 to infinity. F is not 1-to-1, but G is. We will be making use of this nice little fact when we study the trig functions. For the first 3 problems, what we want to do is show that the given pair of functions are inverses. Right, that means first thing we want to do is show that f of g is equal to x. Right? Everywhere we see an x and an f, we're replacing with x plus 3/2. Two over 2 is 1. So we're left with x plus 3 minus 3. 3 minus 3 is 0, which means we're left with x. Now do the same thing. We want g of f. Right? We want g of 2x minus 3. Everywhere there's an x in g of x, replace it with 2x minus 3. Negative 3 plus 3 is 0. Left with 2x over 2. 2 over 2 is 1. Left with x. So this pair are inverse functions. Right? F is an inverse of G, and G is an inverse of F. All right, now we're going to look at x squared plus 3 for x being greater than or equal to 0, and the square root of x minus 3 for x being greater than or equal to 3. F of g is f of root x minus 3. That means wherever you see an x and f, replace it with a root x minus 3. Square root of x minus 3 all squared. Just x minus 3, right? Negative 3 plus 3 is 0. And we are left with x. Now remember, we were told that x is greater than or equal to 3 for g, right? That means that it's also greater than or equal to 0. So this checks out. Now we want g of f, right? That's g of x squared plus 3. Whenever there's an x in g, replace it with x squared plus 3. Now, since x is greater than or equal to 0, that would make x squared plus 3 greater than or equal to 3. So this is defined. Three minus 3, 0. Left with the square root of x squared. Square root of x squared is what? It's x or negative x. So how would you represent that? Absolute value of x, right? But wait, we're told that x is greater than or equal to 0 for f, which means that's just x. Oh, wait. This shows that these two functions, f and g, are inverse functions. Okay, let's continue on. Negative square root of 4 minus x for x less than or equal to 4, and 4 minus x squared for x less than or equal to 0. So first up, f of g of x. Right, that's f of 4 minus x squared, right? Replace the x in f with 4 minus x squared. 4 minus 4 is 0. We are left with negative square root of x squared. Right? Now, as noted before, the square root of negative x, the square root of x squared is absolute value of x. But we're told for g that x is less than or equal to 0. That means the absolute value of x in this case is negative x. So we get negative x, which is just positive x. Now g of f of x. That would be g of negative root 4 minus x, right? Replace the x in g with negative root 4 minus x squared. We'll get 4 minus the quantity of 4 minus x. 4 minus 4 is 0. We're left with minus negative x, which is just x. Therefore, these two functions are inverse functions. Now, I want to point out a nice property of inverse functions. So f is a function that has domain D and range R. So if f is 1-to-1, that means it has an inverse. So f inverse is a function. The domain of the inverse function is R, and its range is D. In other words, the domain and range of the function switch roles for its inverse function. So for the next few problems, what we're going to do is show that the given function is 1-to-1, meaning that it'll have an inverse function. So we'll go ahead and find its inverse. To show that a function is 1-to-1, what we do is we say, okay, let x1 and x2 be two arbitrarily chosen values such that f of x1 equals f of x2. What we want to do now is show that this necessarily means that x1 and x2 are identical. All right, so 4x1 minus 1 would have to equal 4x2 minus 1, right? If f of x1 equals f of x2. By adding 1 to both sides, this means that 4x1 has to equal 4x2. And then by dividing both sides by 4, we get that x1 has to equal x2. This means that f of x is 1-to-1. That means it has an inverse. To find the inverse, we pick some value y and call it f of x. Right, that would mean that for x minus 1 has to equal y. Solve for x. Always add 1 to both sides. Then we divide both sides by 4. Notice what we just did. We assumed that y was an output, right? So we said y is the output that we're looking for. What we just did is found its corresponding input. Since we've already shown that f is 1-to-1, we know that this is the only value of x that would map to y. What we now do is just flip the roles of y and x. And so our inverse function would be x plus 1 over 4. All right, let's look at the function 2 over x plus 3. What I'm going to do here is write out its domain. Its domain is everything but -3, right? Because -3 would give us a 0 in the denominator. What is its range? Its range is everything. All right, so first we're going to show that it's 1-to-1. So we pick two arbitrary values, x1 and x2, and say that f of x1 is equal to f of x2. Remember, that now means we have to show that it is necessarily the case that x1 be equal to x2. Two over x1 plus 3 has to equal 2 over x2 plus 3. Since the numerators of these two functions are identical, their denominators must also be identical. That means that x1 plus 3 has to equal x2 plus 3. Now, by subtracting 3 from both sides, we get x1 has to be x2. And so we find that our function is 1-to-1 as desired. Now to find its inverse. So we let y equal f of x. That would mean that 2 over x plus 3 has to equal y. Remember, we're trying to solve for x. Do you remember what we would have had to do? x2, you mean multiply by 2? Well, if you multiply by 2, that would give us this. I do agree with the multiplication. Multiply by x plus 3. Now divide both sides by y. And then subtract both sides by 3. While not necessary, what I'm going to do is write this as a single fraction. That'd be 2 minus 3y all over y. So f inverse of x would be 2 minus 3x all over x. And I made a mistake. The range is all reals except for 0. That's my mistake. Right, since we're dividing by x plus 3, and the numerator is a constant 2, there's no way you can get 0 out of that. What's the domain? And what is its range? So what we would have to do it algebraically, right? Remember, is do this. Solve for x, and we go, oh, well, k can't be -3, right? So the range would be everything but -3. Oh, but look. The domain of the original function was everything but -3, right? Which is the range of the inverse. The range of the original function was everything but 0, which is the domain of the inverse. So this is confirmation that the domain and range of the original function flips roles for its inverse. Let's look at x squared minus 9, given that x is greater than or equal to 0. So we want to show first that this is 1-to-1. So we need x1 and x2 to be in the domain of f, so that means that x1 and x2 are both going to be greater than or equal to 0. Need to worry about that. Right, so this means that x1 squared minus 9 has to equal x2 squared minus 9. Add 9 to both sides. X1 squared has to equal x2 squared. You take the square root of both sides, you wind up with absolute value of x1 has to equal the absolute value of x2. But they are both greater than or equal to 0. Which means that x1 has to equal x2. That means that for this restricted domain, our function is 1-to-1. If we didn't have this condition, is there a way for this to show it's 1-to-1? Well, that's what we just did. Technically, no. This would give you an idea, right? But to show it's not 1-to-1, you have to find two values, x1 and x2, that are different, but yet f of x1 equals f of x2, right? So what I'll do is I'll say, let's pretend that this condition isn't there, right? So we'll say that the condition that x is greater than or equal to 0 doesn't exist, right? So it's just all values of x. What I would do is I'd say, okay, let x1 be 3 and let x2 be -3. F of x1 would be 3 squared minus 9, right? Which is 0. And f of x2 would be -3 squared minus 9, which is also 0. So what we just did here is found a counterexample. Well, if x2 is 4, then you'd get 16 minus 9, which is not 0. So that's not a counterexample. You want to find two different values that evaluate out to the same thing when you plug it into f. Right, but this work over here would give you an idea of how to do that, right? Because look, this says the absolute value of x1 has to equal the absolute value of x2. If x can be any real number, then you just have to find two different values who have the same absolute value, right? So positive and negative of any number would be your counterexample. It doesn't have to be 3 and -3. You could have used 4 and -4, right? Or 8 and -8. But this is how you would mathematically show that it's not one-to-one. You find a counterexample. Right? Does that make sense? Right. So as I just said, if that condition wasn't there, right, I have a counterexample show it's not one-to-one. So that condition, x being greater than or equal to 0, is very important. Right, now let y equal f of x. Specifically, y has to be in the range of f. Right, x squared minus 9 would equal y. Solve for x. X squared would have to be y plus 9. Which means the absolute value of x would have to be the square root of y plus 9. Right? But remember, x has to be greater than or equal to 0. Right? So that means that x has to be the positive square root of y plus 9. And so our inverse function would be the square root of x plus 9. F of x is 4 plus the quantity x plus 3, given that x is less than or equal to -3. Also, we're going to take note that x plus 3 is going to be less than or equal to 0. Right, because x is less than or equal to -3. Subtract 4. Take the square root. But this would mean that negative quantity x1 plus 3 would equal negative quantity x2 plus 3, right? Since x1 is less than or equal to -3 and x2 is less than or equal to -3. Right, that's using the fact that both x1 and x2 are less than or equal to -3 and this note. Multiplying both sides by -1. And then subtracting both sides by 3. We get x1 has to be x2. And so we have that f of x is 1 to 1. Then we're going to say y is equal to f of x. That means that 4 plus the quantity of x plus 3 squared has to be y. Subtract both sides by 4. Take the square root. Right? But remember that x is less than or equal to -3. So x plus 3 is less than or equal to 0. So its absolute value would give you the negative. All right, so we need to take the negative square root of y minus 4. Now subtract both sides by 3. And so our inverse function would be -3 minus the square root of x minus 4. So the determining factor is if you assume that f of x1 equals f of x2, then x1 has to equal x2, right? So the fact that this was 1-to-1 was because of the condition. Right? Otherwise, like above, right here, we have something like this. Right? If we didn't have the condition that x was less than or equal to -3, you could have that x1 plus 3 is equal to plus or minus the quantity of x2 plus 3, which would not lead to x1 being equal to x2. Right. So as you said, right, that condition locks them to both having to be negative, which now means, of course, you'll get that they have to be the same value. Are there any questions?